Behind this paper, I've written the private key for this Bitcoin address here. At time of recording, that address had over 0.01 Bitcoin in it, worth over $700. You can look it up on a blockchain explorer yourself to verify. I will reveal this key later in the video, but before I do, we need to talk about what Bitcoins are and how they work. And first, we need to understand one-way functions. Qualitatively, a one-way function is a function that is easy to calculate in one direction and hard to calculate in the reverse direction. Formally, easy means can be done in polynomial time, and hard means can only be done in non-polynomial time. Let's take a look at an example of a one-way function. Multiplication can be done in polynomial time. When done longhand, multiplication should scale as the square of the number of digits. So let's time myself solving a 3-digit and 6-digit multiplication problem. So that was 1 minute and 16 seconds. And now let's do a 6-digit problem. Okay, so that took 4 minutes and 39 seconds. So about 4 times as long when I doubled the number of digits. And I may have made a mistake in the calculations here. I'm not great at longhand arithmetic, but the point of the amount of time that it took to do the multiplication is sort of what mattered here. Now there are other algorithms that can do multiplication faster than n squared, where n is the number of digits. But what's important here is that we showed that we can do multiplication at least as fast as n squared. So it will be polynomial since n squared is polynomial in the number of digits of the number. Now let's assume that the two numbers we're multiplying together are prime numbers. Let's call them P and Q, and we'll call their product N. Now by the fundamental theorem of arithmetic, we know that P and Q, since they're prime, are the unique prime factorization of the integer n. Now, if we're given P and Q, we know that we can solve n in the number of digits of P and Q squared time, and that's polynomial. But how difficult is it to recover P and Q if we're just given n here? And it turns out that that problem of prime factorization is hard. And that's hard in the formal sense, in that the fastest known algorithm scales non-polynomial in the number of digits of this number here. For very large numbers n, like larger than a Google, the fastest known algorithm for prime factorization is the general number field sieve, and its runtime scales according to this formula here. Now it does look like it's an exponential, but because of the logarithms within the exponential, it's actually technically faster than exponential time, but still slower than polynomial time. So it's still a non-polynomial time algorithm. So let's just take a look and see how fast we can multiply some prime numbers and then how long it takes to do prime factorization. So I've picked these two numbers, P and Q, which are both prime. And now if we just multiply them together, we get their product, n. and we can time how long it takes to multiply these numbers together using the Python timeIt library. So I've already gone ahead and typed this out, and we're just going to run it 1,000 times and take the average. And so we just multiply that by 1,000. We can see it's taking less than 0.2 milliseconds to multiply these two numbers together. And they are 53 and 55 digit integers. And that makes n 108 digit integer. So how long does it take to do prime factorization on a 108 digit integer? Well, running on my desktop computer for this particular n, it took over 17 hours. And in fact, we can take a look at the RSA factoring challenge. Was a challenge put forward by the RSA Laboratories company to test whether or not prime factorization truly was a hard problem, that no one really could do it. And while it's not running anymore, they offered monetary prizes, so that way people would be incentivized to publish the factorization of the numbers they put forward. And you can see that these 100 decimal digit numbers back in 1991 took hours on what were the most advanced computers then. Better computers than I have can do it in much less than 17 hours. But these larger numbers, these larger RSA numbers, like this 617 digit number, has yet to be factorized because no one can do it. And if we look at the 250 decimal digit one, which has been factorized just in 2020 on the super advanced computers with 2,700 CPU core years, it took a very long time, but we can do the same method that we just did to see how long it would take to multiply these numbers together. Grab this second number here. So we're just not going to multiply them together once, but 1,000 times. And, takes fractions of a millisecond. So this means that multiplication of prime numbers and then prime factorization is a one-way function. So in polynomial time, you can very easily multiply two prime numbers together. But if those prime numbers are large, then factoring the resulting integer is hard in the sense that it takes non-polynomial time. And so this is an example of a one-way function, a process which is very easy and fast to calculate in one direction, but very difficult and time-consuming to calculate in the reverse direction. And so the Bitcoin infrastructure could have been built using RSA encryption, which is sort of the term named off of the authors who came up with it, with this prime factorization model. But it turns out that the size of the numbers that you need in order for RSA to be secure are pretty big. So you have to use these at least 2048-bit numbers, 617 digits. And while that could be done, it's a little cumbersome. And so there are faster or more efficient one-way functions that we could use, more efficient crypto systems. And one such alternative uses elliptic curves. And this is the crypto system Bitcoin uses for its public and private keys. An elliptic curve is any curve of the form y squared equals x cubed plus ax plus b for some numbers a and b. And the different choices of A and B give rise to different elliptic curves. So just looking on Wikipedia here, here's a plot of some examples of elliptic curves with different values of A and different values of B. And you can see you've got these different plots here. Now, the one-way functions that we're going to use on this elliptic curve involve addition and multiplication of points on the curve with other points and multiplication with scalars. So I've written a little script here to help us visualize how this works. So this function here is y squared equals x cubed plus 7, which is the specific elliptic curve used for the Bitcoin infrastructure. So if we have some point on the curve, which we'll call P, so this is just a point where the xy coordinates satisfy this equation, and we want to double that point, so multiply it by 2. The way that we do that is we take the tangent of that point, the tangent on the curve of that at that point, and we look where on the curve that this tangent line intersects the elliptic curve, and the properties of the elliptic curve are such that there will only be one such intersection. And then we mirror that over the x-axis, and that point there we define as the doubling 2 times our original point. So we have 2p there, and we can continue this process. So if we want to double 2p to get 4p, we'll just take the tangent, look at where that intersects, mirror it over the x-axis, and that's 4p. Do it again. We've got this one intersection point, mirror it, that's 8p. And then maybe one more time, let's mirror that, or let's take the tangent, find the intersection, mirror it, and that will be 16p. So this is the process of doubling a point. And now let's investigate the process of adding 2 points on the curve. So let's say we have these 2 points, they happen to be the 1 and 2p from before, and we want to add them. Well, the way we do that is we draw the line that goes through the 2 points, and the properties of the elliptic curve are such that there will only be one other point that is an intersection between this line and the original elliptic curve. And again, we reflect that over the x-axis, and we define that as the addition of those 2 points. So this is how you would find 3p given 1p and 2p. And now let's say they don't have to be sequential. Let's just add the 3p to 8p that we calculated before. So we take that line there, find the intersection, mirror it over the x-axis, and that gives us 11p. There's some really good animations of this process over on this website that I found, curves.xargs.org, which I'll link below. There's also a GitHub of the code used to produce this, which I'll also link. And so let's just take a look. So here, this person is defining elliptic curves again for us and showing us different values. Here they take a specific elliptic curve that actually is disjoint in this way, but all the math works the same. And they go through with maybe better animations than I was able to show us how they're adding these points. And so it's very informative to watch them go through this process and read along what's happening. And then they introduce the topic of finite fields in mathematics. So this is when we're doing like modular addition and multiplication. And if you're unfamiliar with that process, this is sort of a helpful thing to look up and learn, or to refresh yourself. I think it's a pretty good demonstration. But just assuming that you already know how to do this sort of arithmetic over a finite field, i.e. doing modular arithmetic, let's jump ahead to this animation. So this is sort of the important one, which is that the Bitcoin, the curve, the elliptic curve that's used in Bitcoin is actually not over all of the real numbers, which is what we were showing before, but is over some finite field. And we'll take a look at the specific field in a minute, but it's a very, very large field. And so you actually don't get this continuous curve of points, you get individual points. So this is a much more scaled down finite field, just over 61 points, just with 61 points. But the math works out the same. So when we want to double P, there's some concept of a tangent, and we just fall along that curve. But you can see that the line will wrap around until you finally intersect another point on the curve and then mirror over the x-axis. And the addition of points works the same way, where now you draw the line between these 2 points and you keep wrapping around until you intersect another point, and then this curve will be symmetric about the x-axis, just like in real space. And so you take the point that's reflected over the x-axis. And so this is how you do that addition and doubling in this finite field. And so if we wanted to find, let's say 10p, you would just go through the process that has just been demonstrated while I've been talking through this animation. It turns out that for the finite fields, this means that we can go up to 61 as the multiplication to this point p before we start repeating. Now you can actually go a little bit faster. So this is a helpful demonstration as well, where they're showing how to get to 184. Well, you don't have to start with 1 and add all the way to 184. They just doubled to 128. And then we can see here they added to 56, and then they just add those 2 numbers. So there's a pretty fast way to get from p to some multiple of p within the finite field. And so it's this process of taking some point on this elliptic curve, p, and multiplying it by some scalar, which is how Bitcoin keys work. Specifically, the number that you multiply that point p by, that number is your private key as an integer. And when you multiply it by that point p, the resulting point that you get, those xy coordinates, those are the public key corresponding to the private key. So here is the elliptic curve for Bitcoin. Again, it's that y squared equals x cubed plus 7, but it's over some finite field. So instead of f61, like we saw in those animations, it's fp, where p is this really big prime number here expressed in hexadecimal, and here's what it would be in decimal notation, but just as a formula. And this is the point in hexadecimal that is the p. They call it g for like the generative point. And they're just using different formats here. This 02 means I'm just giving the x coordinate. This 04 means I'm giving the x coordinate and the y coordinate, but we don't always have to provide the y coordinate because we can just calculate it from the elliptic curve equation. And the order of this finite field, so actually I said before that with f61 you could only generate 61 points. That wasn't true. There's a different measure of the order, and they're not always necessarily the same. And for the sec p256k1 curve used by the Bitcoin algorithm, that is given by this n value here expressed in hexadecimal. So it's some huge number. And so that's the total number of private keys that there can be in the Bitcoin blockchain. So I've gone ahead and written some code to do these calculations. Basically, I made a class for a point and a class for a curve, which just contains the properties a, b, as well as that generative point g, and this p that is essentially you're doing the modular arithmetic over making it the finite field. And then I've hard-coded in that sec p256k1 curve here at the bottom. So let's go ahead and play around with this a little bit. So here's our curve. Here's the generative point G. So this is the x and y coordinate here of that point G. Now let's just get the point itself. I guess I'll keep it capital. So now we have a point here, and we can do the arithmetic on it. So we can do G plus G, and this gives us another point. So there's the x coordinate, there's the y coordinate when I added G and G together. We can also do 2 times G. And we can see that the x and the y coordinates are the same. Now we can also just do some ridiculously large number. It doesn't have to be as large as the integers used in the RSA crypto system, because the elliptic key or the elliptic curve crypto system just happens to be a little bit more difficult, even within the, not differentiating it between like polynomial and non-polynomial, but the non-polynomial algorithms are just even a little bit more difficult, so it's equally as secure at smaller key sizes. So just mash the keyboard here, multiply it by G. You know, it took fractions of a second. It's really fast. And we can take a look to see, this just gave us some other point on the curve. These are the x and y coordinates. So these x and y coordinates would be the public key associated with the private key 2, 8, 3, 4, 7, 6, 5, and so on. Now, in terms of the one-way functionality of this elliptic curve crypto system, the important part is that this multiplication to get this new point, which, you know, maybe let's call Q. So calculating Q is almost instantaneous. But if you were just given Q, if someone just gave you Qx and Qy and said, here are the xy coordinates, or even just the x coordinate, because you can recover the y coordinate just by using the elliptic curve, and were to ask, okay, what integer value here was multiplied by G to get these x and y coordinates, that is a hard problem. Specifically, it is a problem which can only be solved using a non-polynomial algorithm. And so that is what makes the elliptic curve crypto system also a one-way function. It's why we're able to generate randomly this private key and calculate the public key nearly instantly. But if we share the public key, no one can figure out what the private key is, at least not in any reasonable time. You know, these are with current systems, what's known about the most advanced supercomputers. They're the kind of things that would take billions of years to work out, unless there is some significant advancement in computational power or in the mathematical understanding of how the elliptic curve crypto system works, which would allow a new algorithm that would be polynomial, scale polynomial in time, as opposed to non-polynomial. Okay, time for the big reveal. Here's the private Bitcoin key. In wallet import format, it's a little long, so I had to write it on 2 lines. But here's the private key that is associated with this public key that we saw has 0.01 Bitcoin associated with it. So now, why am I so comfortable sharing with you the private Bitcoin key when there's over $700 at stake? Well, there's something about this particular private key that's special. So first, let's show that this is in fact the private key, which is associated with this public key. And then let's talk about why it's special. So first, let's just sort of show that this private key I just revealed, which was in wallet import format, corresponds to that Bitcoin address, which we saw in the Bitcoin Blockchain Explorer does correspond to 0.01 Bitcoin over $700 at time of recording. So I'm just going to use this library called Cryptos. I'll include a link in the description to the source code if you want to check it out. But so we just let it know that we're using the Bitcoin format, and then with wallet import format to adder, and we put in that private key, and we can see that it corresponds to the public address that we looked up in the Blockchain Explorer. So we had just talked about how this private key is actually just some integer multiplied by that generating point G on the SEC P256K1 elliptic curve. So how do we get from this wallet import format here that I've revealed to figure out what is that integer and to see, as I promised, that there is something special about this private key? Well, if we look at the wallet import format and how that's constructed, basically we take some integer expressed in hexadecimal here, and you add some prefix which tells it something about the blockchain. So specifically, we're using the mainnet, not testnet. And so we add this 80 in front of it. And then that's really it. It's just that in base 58 format, but we add this checksum to make sure that there wasn't some mistake in that value when entering it, to make sure you don't accidentally, hit the wrong key and get a typo. And by doing that, we just do the SHA-256 twice of this value here, and then take the first 4 bytes and tack it on at the end before we cast it into base 58 format. So then going from the wallet import format back to the hex value, we just sort of do that decoding in reverse after dropping the checksum. So let's take a look at this value here. So we have to figure out which part of this value here, which I'll call key, is equal to the checksum. Or sorry, first we have to decode it from base 58. So let's import base 58. And decode it. So we've got our value here. Now it's expressed in this sort of bit format. So if we want to get it into hex, we'll just save this as some integer I from bytes. And I think we have to specify the endian notation. Oops. Is this? No, maybe it's just an argument. Yep. So now we have our value I. And now we want to convert that into hex. And so this gives us our hex string. And now we have to look at which part is the checksum. So it's the last 4 bytes. And so in hex, each byte should be 2 characters. So for that should be 8. So 1, 2, 3, 4, 5, 6, 7, 8. Another way that we could do this is to just store the hex and then as a string, but we want to get rid of this 0x at the beginning, and then actually that 80 at the beginning is just telling us it's the main net, so we want to get rid of those as well. So we want to start at the 0, 1, 2, 3, 4, and then go to the -8th position, and we'll cast that as an int. So there you go. Our key was the value 0. And you could also start from 0 and just make sure your hex string is padded and do the same calculation in order to go from private key to the wallet import format to make sure you get the same value. But so this is what was special about this private key. It is just the integer 0. And what's special about that is if we look at the SecP256K1 elliptic curve and we multiply the generative point G times 0, we will get the coordinate 0, 0, which is not on the elliptic curve. It's not a valid public key. So if we look at the way that the Bitcoin address is generated from the public key, in this case it will be 0, 0, those coordinates, we can see in this image here, and then we'll kind of look at the math, but we start with the X and Y coordinates expressed as 32 bytes. So in this case, it will just be 0, 0, and then we perform a SHA-256, and then this other hashing algorithm, RIPE-MD-160, and then we do another set of two SHA-256 hashes to get a checksum and lump them together, and that's how we're getting this Bitcoin address. So the address is actually different from the private key. The private key are the XY coordinates, and the address is this hashed version of it. And there's a little bit of added security there in the sense that in order to go from a Bitcoin address to the private key, you wouldn't just need to figure out how to get from that XY coordinate of the point on the elliptic curve to figuring out what the integer which was multiplied by the point G. You would also need to undo the hashing. You would need to figure out what values were hashed in order to, because those are the public key, in order to get that address. And that is a more or a different type of difficult cryptography problem. So it kind of has this double layer of security until you spend money from, or Bitcoin from that address, because in order to do that, you actually have to reveal your public key, and then you could figure out what the public key is associated with that address. And so we could look here to see when you have points, how you're getting the calculation of doing these hashes, and you can walk through these examples where they have some private key and then they get the public key and then they do the hashes to get down to the address, which again is encoded in base 58. So we won't do all of that. We'll just use that library Cryptos again, but we will check that if we do our private key, and first we'll go to public key. Key, again, was this key right here. And we can see that it corresponds to this public key, which has the 04 designation at the front, telling us that it is both the X and the Y coordinate and that it's all zeros. I think this would also work if we just gave it 0. Yeah, so then it's giving us the 0.00, just to really emphasize that that is the point that's associated with this multiple of 0 times that generative point G. Wonder if we can even see G. No, okay, that's not in the library. But so then we can go from the public key to the address. So I'm doing this in kind of 2 steps, but we can see we get that public key again, and then this library also would let us just go straight to the address. So we see that the Bitcoin public address that I showed on the whiteboard before that has this over $700 associated with it, the private key underlying that address is the integer 0, which is not a valid private key, because 0, 0, right? So in the y squared equals x cubed plus 7, if you plug in 0 for x and 0 for y, those two equations won't be equal, right? We'll get x squared on one side. So I'll do an assert here, or right, we're getting false because we're getting 0 equals 7. Now, one thing I'm not going to discuss in this video, but that I alluded to just a moment ago when I said that it was really the public key that was used to control the funds, and the address, that hashed version of it, is just sort of an added layer of security. The way that that is done is using something called the elliptic curve digital signature algorithm. So basically on the blockchain, there is knowledge of the fact that this public address has a certain amount of Bitcoin associated with it. And when you want to transfer that Bitcoin, to spend it, in a sense, by transferring it to another wallet, you basically say like, okay, here's the other wallet I want to transfer it to, and you just give the public address there. That's just some string. Nobody knows the private key, and if it's a new address, people don't know the public key either. They just know the address. Then share what the underlying public key is to the address that you're transferring the funds from. Bitcoin miners can verify by going through that hashing that, okay, this public key actually does correspond to this public address that we know on the blockchain has some amount of Bitcoin associated with it. And then you perform this digital signature algorithm. You create this digital signature which corresponds to that public key that you have now shared that's associated with the address. And the mathematics are such that the only way you would be able to generate the digital signature is if you had knowledge of the private key which generated that public key. But importantly, you don't actually have to share the private key. You can just show this algorithm or this signature, and people can verify from the public key that, okay, you must have known the private key associated with this public key to generate that signature, but you don't have to reveal the private key. So we're not going to go into that in this video, maybe in a future video, but these digital signatures are sort of a clever way to show some verification to orchestrate all of the transfers of funds on the Bitcoin blockchain. Now, there's one more interesting thing about this public key, for which there's over $700 in Bitcoin, and that's that we said that this was the private key that gave rise to this public key. But really what we should have said was that this is one of the possible private keys that gives rise to this public key. There's an interesting artifact in the way that the blockchain works, that the keys, since there is a hashing function for which there could be collisions, now they're very rare, and so we assume that they don't happen, but there could be multiple private keys that give rise to the same Bitcoin address, even though they have different underlying public keys, but that hashing of the public key could have a collision in the address. So while we know that this private key that corresponds to 0, which isn't a valid private key, would give rise to an invalid public key at the point 0, 0 on the elliptic curve, which isn't on the elliptic curve, that's why it's not valid, but then would hash to this public Bitcoin address. There could be other valid private keys which are associated with some other point, some valid point on the elliptic curve, that then when they hash them have a collision and are associated with the same Bitcoin address. And so it's possible that there are valid private keys out there that someone knows or doesn't know that could be discovered that would give rise to the same address. And then the person that had knowledge of that private key actually would have access to the funds in this public address. So this doesn't mean that these Bitcoin are necessarily lost forever. It's just very probable that they will never be recovered. And so in that sense, maybe this video wasn't as clickbaity. Maybe it is possible to get access to that $700, and who knows, maybe it'll be you. Well, thanks so much for watching, and I'll see you next time.